can't just, for many series, automatically say, oh, I can come up with a guess point. Some jiggly-pokery to prove a theorem that says this type of series converges. When we prove a type of series converges, we study the sequence of partial sums. We show that says that limit exists then. And so you can give the limit of the series, the infinite series a name, and then you can approximate it by taking like the 1,000. What's the limit of that? What can you say about the limiting object of this? We'll study the sequence of partial sums. So that sequence satisfies some condition that's like equivalent to convergence, either pointwise or uniform. Limit to be continuous. Condition which implies convergence, either uniform. Presumably, I already have one in mind. Well, I guess I can spoil it by saying, well, look at the title of today's lecture. I will introduce the uniform and pointwise Cauchy criteria. Well, here I'm saying criteria instead of criterion, because criterion is the log. There are two of them. So let's talk about the Cauchy criteria. And so this definition should be reasonably obvious. Oh, wait, should we start with the pop quiz? The pop quiz. Complete for me the following definitions. What does it mean to say that a sequence of functions is pointwise convergent? What does it mean to say that a sequence of functions is uniformly convergent? Actually readable? The definition of that. Well, epsilon greater than 0, such that of fn of x that. And that's exactly what it should mean, because that's the same thing as saying, and I'm writing this next line for a reason. So I'm going to reference it in a moment. For all x, this sequence of numbers converges. And that's generally whenever anyone says something is pointwise whatever, that's what they mean. For every possible input satisfies this condition. And there are advantages and disadvantages to both. An advantage to this one is it's like the obvious definition. Like this is what, if you say something converges, this is what the most obvious thing you could possibly mean is. We've seen that there can be some bad behaviors, though. Continuous things can converge to discontinuous things. You can not be able to flip the order that limits should come in. But as soon as you have uniform convergence, you do get those things. Something equivalent to convergence that doesn't make any reference to what the limit is. I'm going to come up with the Cauchy criterion. And, well, we already know one. Comes of this. For a sequence of numbers, we have a condition that's equivalent to being convergent. It's called being Cauchy. So there's definition one. 8.3.1. A sequence of functions is pointwise Cauchy if for all x in u, this sequence of numbers is Cauchy. So this is the same philosophy as going between these two. A thing is pointwise whatever if it satisfies that thing for every input. Let's expand that definition though. That means that for all x in u, how many people remember the definition of what it means for a sequence to be Cauchy? Nice. Cool. But there's just expanding out what the word Cauchy means. The lighting is particularly bad today. So that means if you want to show something is pointwise Cauchy, you would consider any x in u, you would consider any epsilon bigger than 0, then you would have to come up with a choice of big N. What can that big N depend upon? What will not come as a surprise. To go from pointwise convergence to uniform convergence, we just did whatever we needed to make N be the same for every choice of big X. N cannot depend on big X anymore. How do you do that? You just declare X later. So how would you change this blue definition to get a uniform version of it? Yeah, you could move it there, or you could move it there, you would get something equivalent. Get it past there exists an N. So let's do that. A sequence of functions is called uniformly Cauchy if, for every epsilon bigger than 0, there exists a big N such that for all m and n bigger than big N, and for all x in u, alright, that for all x could be there, it would be the same definition. So the first is something that it seems like just a warm-up, but it is something that I'll actually use. Presumably the pointwise thing, nope, the uniform thing implies the pointwise thing. And the idea of that proof even seems pretty obvious. If you can use the same n for every x, then just use that n for each x. And so that hopefully is very believable. We can go through and read the proof if you want. And what's the whole point of the Cauchy criterion? It's that it implies convergence. In fact, it's equivalent to convergence. Now, the other thing that I'm going to do today, Theorem 8.3.4, if you have a sequence of functions, then pointwise convergence, if and only if pointwise Cauchy. In fact, that will be reasonably quick and I think fairly obvious once we see the proof written down. The more important thing is if you have a sequence of functions, uniform convergence is equivalent to uniform Cauchiness. People feel okay about this plan? Groovy. So, first things first, proposition 8.3.3. If a sequence of functions is uniformly Cauchy, then that sequence of functions is pointwise Cauchy. Should we go through the proof? Is there a demand? All right, so let's read it through. Let's let f sub n be a uniformly Cauchy sequence of functions. That's the right assumption, I think. You want to say uniform convergence sequence of functions implies pointwise convergence sequence of functions. All right. So you want to show f sub n is Cauchy, not convergent. You want to show f sub n is pointwise Cauchy. So if there are any x in the domain and any epsilon bigger than 0, then you need to come up with a choice of big N. I think that's it in order 10 to back just erased. Let's consider any epsilon bigger than 0 and any x in the domain. The domain is U, not R. And know that the sequence of functions is uniformly Cauchy. There exists a big N such that for every bigger than big N, and every y in the domain, U not R, all right, so there's a choice of big N. Now so we considered any x, we considered any epsilon, we came up with a choice of big N. Now we should consider any m and n bigger than big N and see what we can do. That inequality already holds for absolutely every input. For every y and u, we get this conclusion. Is x a particular input that we could plug in? Yeah, so I just didn't want to use the same variable. Use x again. No, it's only supposed to be. That makes more sense now, right? I know that for absolutely every choice of y, that inequality holds. Right now we have for all y in u, this inequality holds. Since x is in U, conclusion? People feel good? If you know a universal statement is true, then you can use it to get a particular statement to be true. We start with the consider any epsilon bigger than 0, and then to consider any x. Then did we come again? Yeah, we don't. We have an n bigger than big N, and then we got this inequality. If you care about Cauchy, you should care because it should be the same as convergence. Yeah. Okay. All right. Let f sub n be a sequence of functions, then f sub n is pointwise convergent if and only if it is pointwise Cauchy. And for sequences of numbers, that says that a sequence of numbers is Cauchy if and only if that sequence of numbers converges. Do that. Let's let f sub n be a sequence of functions, and first let's suppose that f sub n is pointwise Cauchy. Pointwise Cauchy. We input they're close together. They're Cauchy. Numbers is Cauchy. People feel okay about that? That is definition 8.3.1 in action. What's the whole point of Cauchy sequences of numbers? Numbers converges. Sequence of numbers, f sub n of x converges. I will now define f of x to be the limit as n goes to infinity of that sequence of numbers. F of x. Let's do that. By the very definition of f of x, namely f of x is the limit as n goes to infinity of f sub n of x, we now have that for every x in U, well, tell me what goes there. For absolutely every x in U, what's the limit of n of x? Oh, neat. Have we just shown that for every x in U, the sequence of numbers f sub definition of pointwise convergence? With the proof done, do you think the other half will be pretty easy as well? In fact, I think it'll be easier. Let's do it. So let's suppose that f sub n converges, let's suppose that f sub n converges pointwise. Let's let f be the pointwise limit. In fact, I think we can all of this. Suppose f sub n converges, no, we'll leave it. Let's let f be the pointwise limit. For absolutely every x in U, what can you tell me about f sub n of x based on that? What does anything mean? Converges to f of x. So, convergent sequences of numbers are Cauchy. What can you tell me about the sequence of numbers f sub n? Oh, neat. Have we just shown that for every x in the domain U, the sequence of numbers f sub n of x is Cauchy? It means to be pointwise Cauchy. I was going to point at the bottom. Definition's not on the bottom. One we're really going to care about anyway. Pointwise limits can still have bad behaviors. We want power series to have good behavior, and we want to be able to prove it. Let's let f sub n be a sequence of functions. Then, f sub n is uniformly convergent, if and only if f sub n is uniformly Cauchy. Let's try to prove this. It was a while ago that we proved the Cauchy criterion for sequences of numbers, right? What we're about to do will be basically the same. And that might not be helpful because that was a while ago. Let's try to do it. So, let's suppose that f sub n is uniformly convergent. Let's let f be the uniform limit. Is uniformly Cauchy. I'll remind myself this on the board. For all epsilon bigger than 0, there exists a trace of big N, such that for all m and n bigger than big N, well, the proof has to begin. I have to start by considering any epsilon bigger than 0. Functions is uniformly convergent. Does that in fact give me a choice of big N? I have positive epsilon. So there exists a big N. Considering the epsilon bigger than 0. Since f is the uniform limit of f sub n, there exists a big N such that for all little n bigger than big N, and for all x in the domain U, absolute value of f sub n of x minus f of x is less than one divided by 2 trig at some point. Let's divide by 2. We'll code it. We can change it if we need it. Do I know something like, my eventual goal is f sub n of x? I can add that. Absolute value, f sub n of x minus f of x plus f of x minus f sub n of x by adding and subtracting f of x. And you know what do next? There's going to be like a triangle inequality argument. I'll figure out if the bounds that I have are good enough. If it's not good enough, then I'll divide by something that's bigger than 2. So by the triangle inequality, this is less than or equal to absolute value, f sub n of x minus f of x, plus absolute value, f of x minus f sub, one of those should be an m, right? F of x is less than something? Awesome. On over 2 plus epsilon over 2. Is division by 2 the right choice? Seems to be. Division by 3 would also have been an acceptable choice. 2 epsilon over 3 is also less than epsilon. That would have made us happy as well. Feel pretty okay? In the proof of the Cauchy criterion for sequences of numbers, this was the easy direction there also. Convergence implies Cauchy is really easy because you have like the limit that you can just point to and say, well, I'm getting close to that, so I got to be getting close to each other. Let us assume that the sequence of functions is uniformly Cauchy and try to get that this thing is uniformly convergent. So there will be some tricks involved, including that warm-up. So let's suppose that f sub n is uniformly Cauchy. By proposition 8.3.3, what can I conclude about f sub n? Why is Cauchy? So I've just thrown out a bunch of information, but this will give me something. At theorem 8.3.4, what do I know about pointwise Cauchy sequences? Oh. Wait. Nice. So this sucker is pointwise convergent. It has a pointwise limit. Do you think that's a pretty good guess? Prove a thing is the limit. Coming up with a that flow like out of the woods. We know that uniform is a stronger condition than pointwise convergence. We need to improve this convergence somehow. Strategy. We want to show f sub n converges to f uniformly. What do we need to show? We need to show this. Let's do it. So let's consider any epsilon bigger than 0. I need to come up with a choice of big N. I can't use pointwise convergence to come up with a choice of big N because that would require me to make a choice of x, and then the N would depend on x, but N isn't going to depend on x, so I can't do that. But I do know that this thing is uniformly Cauchy. Does that give me a choice of big N? Consider any epsilon bigger than 0, since f sub n is uniformly Cauchy. There exists a big N, such that for all little m and little n bigger than big N, and all x in u, the absolute value of f sub m of x minus f sub n of x is less than. Now, presumably there will be some like epsilon divide by something game going on. Right? Divide that epsilon by something right now? All right. That, you're probably not wrong. We don't have a proof yet. If the idea has any player of walking, presumably dividing by 200 would be good enough. Something like the space of all functions. Effort to figure out, you need like density function on the space of all numbers. That is definitely not something that I should get into since I really only have like 5 minutes left. Because I want to do these today. So let's see. This is the thing that I have right now. I can just like plot across. My eventual goal is absolute value of f of x minus f sub n of x is less than epsilon. There's my goal. But here's the strategy that I'll try to do. I'll listen to something that says f sub n is between two things. Following this equality for f sub m, I see that for all m and n bigger than big N, f sub m of x is less than f of f sub n of x plus epsilon over 200. F sub n of x, minus epsilon over 200. People feel pretty good right now? Infinity. If you take the limit as m goes to infinity, what does this approach? It goes to infinity, this goes to what is equal to. F sub n of x minus epsilon over 200 is less than or equal to f of x is less than or equal to f sub n of x plus epsilon over 200. Thing that's written right there look really, really close to being this. Yeah, I guess, except there's a loose inequality where you want a strict one. And there's a division by 200 where I don't care about division by 200. But those two things actually line up pretty well together, don't they? So let's go to the next step. Properties of absolute value then. That means that the absolute value of f sub m, f sub n of x minus f of x is less than or equal to epsilon over 200. Is that less than epsilon? Complete the proof? If you came up with this proof, would you then want to go back and like erase two of those zeros? Let's see if the 200 is a reasonable thing to do and it works, but when you're the reader reading it, like, you'll reach the end and you would say, well, why on earth did they divide by 200? 2 would have walked. End of the choice of acts. Accident you of acting is less than epsilon. This is the honest to God uniform limit. Since epsilon has a uniform limit, it is uniformly convergent. And I will point out now that the homework after printing was revised a little bit. In particular, problem 2. It's still the same logic, but it's the series underlying the so-called Weierstrass monster function. It's called a monster function because it's a function that is everywhere continuous, but nowhere differential. So if you try to take a tangent line at absolutely any point, you can't. Every point is a call. Differentiable isn't so terrible either, but we don't even know what differentiable means, so we can't do that. There's a link to, if you like, just, I think it's just a Wikipedia article about it. Cool. I'm going to stop now. Maria, you said you would be happy to take these off. So let me get these out. Let's go that way. And then straight back. Pencils. Who needs pencils? Don't start filling out anything because you can't fill it out while I'm filling. We want 6. Section number 001 and date may at the top of the upscan sheet. Do not fill in the ID number sections. Use a number 2 lead pencil to mark the upscan form. If a particular item does not apply to this instructor/course, if you had no opportunity to make a judgment about an item, then use E, no option. This upscan is to be completed anonymously. Blacken the circle in the upscan sheet, which corresponds to your reaction to each statement using the appropriate categories. This one. Get it up? Awesome. Okay, and